In part 1, we went over the setup of an Elixir application and wired up our supervision tree. Here we're going to pick up where we left off by adding a navigator module for calculating distances between postal codes and a cache module to improve our performance by using memoization. It would be a good idea to check out part 1 of this to make sure you're familiar with the general application layout. We'll start with our navigator as an ordinary module and first add the methods we need. Our main method is going to be getDistance, where from and to are postal codes. When a private method has the same name as the public method, conventionally it's prefixed with do. To calculate the distance, we'll need geolocation data for both from and to postal codes. For now, since we're just scaffolding this, getGeolocation will just return a 2-element tuple with some numbers, and the getDistance method itself is just going to return a number in order for us to write a test to make sure everything else is wiring up properly. We'll create our navigator test module and save it in test postal code directory. We'll use xunit and alias the module to make sure that we can just refer to it by navigator instead of the entire namespace. The test itself is going to be fairly trivial. All we want to do is make sure when we call getDistance, we'll get the value that we expect it to return. It's actually not going to be doing anything else at this point. When we run our tests, we get warnings about unused variables in our navigator module, but otherwise everything passes. What I would like to do next is to add guard clauses to our getDistance method. We'll add whenIsBinary check to both from and to, which will make sure that this method is only going to get called when both arguments are strings. As you recall, our store module uses postal code strings as keys, so using anything else wouldn't work. Besides running a test, we can confirm that this method works by launching a console. When we call our getDistance method with our postal code strings as arguments, we get back that statically set number that we expect. Passing in our postal code numbers as strings seems like a pain. It would be much better if we can pass in our postal code numbers as numbers and not worry about quoting them every time. This, however, will fail with a no match error because of our guard clauses. We can easily fix it though by adding another method that just deals with integer arguments. We'll add whenIsInteger guard clauses for both from and to, which will now match this method. Now what we can do is take these values and convert them from integers to strings, and once we have those string values, we can just call the doGetDistance again, which will now match the method at the top. We can confirm that this method works by going to the console and recompiling our project and then running the same method again, which this time produces the answer we expect. This is great, but the problem now is that both of our arguments are expected to be either strings or integers, and we can't have a mix of both. We can fix this by moving our guard clauses from getDistance to getGeolocation, which will work because getGeolocation only deals with one argument at a time. Doing this also has an added bonus of getting rid of some code duplication, so we don't have to call integer to string twice in one method. After we recompile, we can expect our method to work for either argument, being an integer or a string. Another case that would be nice to deal with is some kind of a nonsensical argument. Instead of just getting a no match error, it would be better to get an error that includes our input. We can do that by adding a catch-all getGeolocation method that's not going to have any guard clauses and that's going to raise an error no matter what. We can then include our inspected input in the error, which would make debugging quite a bit easier. When we recompile and call our method again, we're going to get an argument error that includes our faulty input instead of a no match error, which is a lot more clear. Now that that's done, we can add some tests that are a little more meaningful. We can have a test for each type of input, where both arguments are strings, where both arguments are integers, and a mix of arguments where one is a string and another an integer. Another test we should have is one that confirms that we get an argument error when we have unexpected input. We can use assert_raise_argument_error and wrap our call inside of the function. Press Ctrl+C twice to exit the console. We can then run our test and confirm that everything works as expected. With our basic scaffold out of the way, we can now get down to business. We'll alias our store module so that we can access proper geolocation data rather than returning this static tuple. Then we'll need a calculate method to actually calculate the distance between two geolocation coordinates. We'll keep the response of the calculate method static because calculating the distance between two geolocation coordinates involves some math that I'd like to discuss first. We'll be working with degrees, latitude, and longitude, which in our case are just plain numbers that look something like this. I'd like to talk about what these numbers actually represent. Latitude and longitude coordinates can be applied to any sphere, not just Earth. If you cut the sphere in half and make the biggest circle you could possibly make, that would be called the great circle of the sphere. If you make a line going from the center of the sphere touching the great circle, that point will have a latitude of 0 degrees. If we place a point directly above this line and measure its angle, that angle would be the latitude. So the maximum latitude any sphere can have is 90 degrees. The latitude at the South Pole would also be 90 degrees, but if we represent that latitude in plain numbers, that number would be negative. So the latitude in the northern hemisphere is positive, and the latitude in the southern hemisphere is negative. The longitude is an angle between the prime meridian and our point. On any sphere, a prime meridian can be chosen arbitrarily. It simply serves as a reference point for calculating longitude, and there isn't anything special about its particular location. So the longitude of our point is just the angle between it and the prime meridian. So the coordinates of our point are 75 degrees north and 20 degrees west. Or in plain numbers, that would be 75 and negative 20. With longitude, west direction is negative and east direction is positive. To calculate distance between our 2 points, we'll be using something called the great circle distance calculation. It works by adding another great circle that goes through both our points and calculate the shortest distance between them by using the trigonometric relationship between the two great circles. This will be an approximation because it assumes that Earth is a perfect sphere, but it will still work quite well for our purposes. This wasn't a comprehensive explanation, so I'll leave some links in the description so you can learn more about it. We'll alias Erlang's math library as math, and then add the Earth's radius in both kilometers and miles. And we'll be using miles as our units here. One thing we need is a helper method to convert degrees to radians, since our formula uses radians and the latitude and the longitude are in degrees. So all we need to do here is multiply degrees by pi divided by 180. I tried to break this formula down into the values that we'll need. We'll need the difference between latitude 2 and latitude 1, the difference between longitude 2 and longitude 1, then we'll just need the radians of latitude 1 and the radians of latitude 2, so we can get the cosines of both latitude 1 and latitude 2. Then we'll need to take the sine of the difference in latitude divided by 2 and take that to the second power. And we'll do the same with longitude over here. Now we'll take the values we got and plug them into our formula. Once we have our value, we can take that and multiply it by the radius, and we'll get the distance and round it by 2 decimal places. When we run our tests, they will fail as expected because we now have actual distance rather than fake distance we've been using before. So what we can do there is just update. Instead of having the exact distance, we can just look for some kind of a floating point number over here. And when we run our tests again, now they should pass. It would still be a good idea to test finding actual distances between actual places to confirm that our formula actually works. I got some driving distances for a few different cities, one for a very short distance, another one for a longer distance from west to east, and another one from north to south. Now, these will be approximate since these are based on driving directions and our geolocation distances are more like flight paths. We'll print the result of our method for each set of postal codes. We'll then use that result to compare it to what we've approximated here. Again, we do not expect them to match up exactly, but it should still be fairly close to what we have here. When we run our tests, we can just grab the values that we get and use them in our assertions. As you can see, the values that we got are not too far off from what we've approximated. What we can do now is change our put statements to assertions for every one of those cities, and we should be good to go. We just need to run our tests to confirm that everything is working properly. And there we go. We now have a module that can calculate distance between two postal codes, which is pretty cool. Next, we'll turn our ordinary module into a GenServer module. We'll need to add a start link method, and we'll name our module Postal Code Navigator. Inside of our getDistance method, we need to use GenServer call, because whoever is going to be calling this method will expect a reply. We'll add our handle call callback and move our doGetDistance method into there. Notice that we didn't have an init method in this GenServer. That's because we only use it for calculations. We really don't care about its state. We can easily replace this state with just an empty list, and it would still work just fine. The init method is actually implied. Now we can add our navigator module to the postal code supervisor. We'll alias it just like our store module and add it as a worker. There's a neat shortcut for aliasing module that if they all share the same namespace, you can just put them in a comma-separated way like this. So now the navigator module is part of the supervision tree. When we run our tests, we get a failure because our error assertions are not being handled properly since the navigator is now a supervised GenServer. So we can't test that a supervised process got an error. What we can do indirectly though is to notify another process when our navigator process goes down and check what the down message contained. So in this case, we'll add a reference to monitor our navigator process ID, and instead of assert raise, we need to catch exit. And what we can do now is assert that our reference received a down message from our navigator process ID, and that message was an argument error. So what we're checking for here is that our reference process that monitors our navigator process received a down message in its mailbox, and that message was regarding our navigator process ID, with the message being the argument error. When we run our tests again, at first it looks like we got another failure. However, if you look closely, you'll see that all 10 of our tests are passing and we have 0 failures. This red output is just a logged error message that happens to come from the GenServer. We can clean this up by adding a tag capture log just for this test so that we won't see that logged error message. So now when we run our tests, the output is going to be nice and green. So our navigator module is good to go. One issue is that this really expensive calculation is going to be happening every time, even though we might be dealing with recurring postal codes. One way to solve that is to add some sort of a memoization or a caching technique, which in our case will be another module. We'll create our cache module and make it a GenServer right away. This will be pretty much a key value store. We'll name this process postal code cache, and since we'll be storing state here, we'll definitely need an init method. Our state is going to be a nested map initially with distance key pointing to another map, so that we can potentially use this module for other caching. We'll start with a setDistance method, where we'll be passing the from and to and the distance, and this will be a GenServer cast since we won't need a reply, so we'll just be setting the distance. GetDistance is going to be taking the from and the to, and it's going to be a GenServer call method. We'll be passing in from and to postal code arguments to our handle call method. Don't confuse them for the from argument that all handle call methods normally get. Our key is going to be a map set, since the order of from and to don't matter, and the distance is going to be the same in either direction. Since we are dealing with the nested state, first we need to fetch the distance map from our state by the distance key. Then we can fetch the actual distance by our key that we generated here. And then whatever we get, we'll put that in our reply. Our setDistance callback is going to take 3 arguments: from, to, and distance. We'll still need to set our key, and then we'll need to update the entire state, so that means we need to use the map update function, so that inside of there we actually set our distance map, and that's what's going to be under the distance key of our state. Now we'll add our cache module to the postal code supervisor, so it's going to be part of the supervision tree, and we'll start up with the rest of the processes that we need. We'll add a pretty straightforward test to this, since all we need to test is the key value store capability of this module. We'll put in an arbitrary key 1 and 2, and some kind of a distance that we're going to store. Then we'll call our cache set distance with both of our postal codes and the distance, and we should be expected to retrieve that distance with getDistance method for postal code 1 and 2. Now we'll just assert that distance equals retrieved distance. Alright, looks like we'll get a failure because we don't have the proper reply in our handle cast method here. So all we need to do is add no reply to this, and we should be good to go. Now that we have a test in place, we have an opportunity for some refactoring. First, we can add a generate key method to remove the duplication for key generation in both handle cast and handle call. It's still a one-liner, however, in case we ever want to change our key, it will be good to do that just in one place. Elixir has getIn and putIn methods that are really nice for working with nested maps. We can just pass a list of keys to the depth that we want to get to, and either get or set our value. So we'll be using that here. And we'll run our test to be sure that we didn't break anything. Now we can go back to our navigator module and add our cache. One issue here is that the cache is based on the postal codes, and we don't even necessarily need to fetch geolocation for them from the store. One way to address this is to separate the concerns from our getGeolocation method into a separate format method. The problem here is that our getGeolocation method is actually doing 2 things. It's formatting our input, and it's fetching the postal code geolocation from the store. If we split that into separate methods, we can have format postal code completely independent from actually getting geolocation. This way we can check our cache before fetching geolocation. Let's make sure that this change didn't break anything, and then move on to adding our cache module. We'll add an alias for it next to the store module, and then add a case statement to check for cache presence inside of doGetDistance method. So all we need to do is pass the 2 postal codes, and if the response is no, that means we need to do all the necessary calculations. And also, after we've calculated the distance, we can then actually set the cache right from here. If the distance was found, all we have to do is just return it. And that should be it. We'll just confirm that everything still works, and we're done. We've built a pretty efficient navigator module that can calculate distances between two postal codes. I think that's pretty cool, and it's going to be really useful for our delivery company. So far this is what our application supervision tree looks like. I'll leave the link for the code and all the other concepts we talked about in the description. In this video, we talked about more practical applications for the GenServer, such as caching and as a unit of calculation. We also demonstrated guard clauses and some more refactoring techniques. I hope you enjoyed it, and thank you for watching.